Discipline is our top priority, but temptations are everywhere.
Oh.
To tackle this challenge, I developed a solution that turns earning treats into a daily achievement: the ChocoVault. This secure, high-tech storage device safeguards my sweet calories by connecting via Wi-Fi to the activity data measured on my Apple Watch. Access to my treats is granted only after reaching my daily activity goal. In this video, I walk you through the major design decisions and the assembly process. I'll also show you how to manage the automated transfer of activity data from the Apple Watch to any network-connected device, along with an overview of the device's operation. Let's begin with the heart of the ChocoVault, the smart lock assembly. For the lock actuator, I selected a standard N20 DC motor with an integrated gearbox. These motors are inexpensive, come in various shaft speeds and voltages, and provided a good starting point for establishing the proportions of a lock assembly. The locking mechanism comprises a pair of strikers and spring-loaded latches that slide within a cavity in the lock body. In the locked state, the latches engage firmly to secure the strikers. To unlock the assembly, a pair of racks and a pinion gear attached to the motor are used. As the motor drives the racks into the open position, the latches retract simultaneously. Because the motor lacks inherent position feedback, adding end-stop detection was necessary. For simplicity, I opted for a non-contact solution. Magnets attached to the racks, as shown here, work in tandem with Hall effect sensors mounted to the control electronics PCB, visible at these two key locations. Additionally, a third magnet is integrated into one of the strikers to detect its presence within the lock assembly. The PCB mounts directly onto the lock assembly and snaps securely into place with dedicated locking features. On the backside, connectors for the power supply, motor, and speaker are visible. Next, let's examine the body of the ChocoVault. The body features a cavity for mounting a DC barrel jack power connector as shown here. It is accessible on the backside of the box. These small features along the bottom of this cavity will be used to route the power cable from the barrel connector to the PCB. On the front, there's an attachment point for a small speaker with sound exiting through a discrete, concealed slot. The lock assembly slides seamlessly into the body's cavity without extra fasteners and is later secured by adjacent components. A similar approach is used for the hinges. Each hinge's bottom half fits into a precisely cut-out slot, ensuring a snug, secure fit. A key requirement was for the lid to automatically pop open once the box unlocks. To achieve this, a dedicated spring-loaded lid pusher mechanism is integrated on both sides. This mechanism uses the two orange linkages shown here, connected to sliders that run along steel rods. The springs, which counteract the lid's weight, will be installed on the steel rods in this area later. To select a compression spring with suitable parameters, I derived the equations governing the linkage movement and transferred these into an Excel sheet. This allowed matching critical parameters such as spring rate and length with off-the-shelf springs. An interior panel is then installed to conceal the mechanical components and provide a sleek appearance. More importantly, it secures critical parts including the lock assembly, slider rods, barrel jack connector and lid hinges using just a few screws. To attach the strikers to the lid, dovetail features similar to those used in the lock assembly and hinges create an extremely durable connection. Here, forces acting on the strikers aren't transmitted through screws. A single screw merely keeps the strikers in place when the box is open. In this cross-sectional view, you can see the magnet on the striker working together with a Hall effect sensor on the PCB to detect the striker's presence within the lock. The integrated electronics are built around an ESP32S3 microcontroller, which simplifies running a web server, performing over-the-air firmware updates and playing WAV or MP3 files. The system is powered by a standard 5V DC supply with an onboard voltage regulator providing the required 3.3 volt rail. A dedicated motor driver IC streamlines motor control, while a mono Class D audio amplifier with digital I2S input handles audio playback. As shown earlier in the CAD model, 3 small Hall effect sensors on the PCB detect the end-stop positions of the locking mechanism. Additionally, a ring of 12 addressable RGB LEDs serves as a status display. The web server on the ESP32 receives activity data from Apple Health as a JSON record, which is then used to display the current activity energy status on the LED ring, mirroring the Apple Watch display, while also managing the locking mechanism. Most of the mechanical components were designed for 3D printing. Throughout the design process, the goal was to minimize waste by avoiding support structures and to optimize part strength. For components subject to significant mechanical loads, such as strikers and hinges, designs were oriented so that the maximum tensile stress runs along the layer lines, rather than perpendicular. As shown here, the strikers are printed flat on the build plate, while the hinges are stacked vertically for optimal strength. After assembling and testing the hardware, a solution was needed to synchronize the ChocoVault with activity data from the Apple Watch. Since direct communication from the watch isn't possible, the data is routed through Apple Health, enabled by the app Health Auto Export, which can be found in the App Store. This app offers various options for automating the export of Apple Health data and supports sending it at regular intervals to web services, online or within a local network. In this case, a new automation for the ChocoVault is created. The process is as follows. First, select the REST API automation type and enter the address of the box on the local Wi-Fi network. Choose Health Metrics as a data type, then specifically select the Apple Watch metrics. The vault is configured to unlock only when the red ring on the watch is completely filled, which represents the activity calories or active energy as referred to by the app. Next, set the export format to JSON. To ensure that the data which is currently displayed on the Apple Watch is synchronized with the vault, the data range must be set to today and aggregation to days. Finally, configure the synchronization interval to every 5 minutes and save the automation. In this example, the red ring on my watch is about 1/3 filled. When the automation is executed, the vault displays the same status after the sync, and the iPhone app will now continuously send updates every 5 minutes in the background. And with that, the complete system is finally ready for testing. First, the vault is loaded with a sweet reward. When the lid is closed, the box automatically locks after 3 seconds and prevents manual opening. Unfortunately, the test requires physical exercise and no volunteer could be found, so I had to take on the challenge myself. Here are 3 hours of exercise in time-lapse.
Yes! Oh yeah!